So let's continue our lesson. Now we'll see another problem. Okay, we have another problem which is saying a loop in the form of triangle, equilateral triangle, which means that every side of triangle is equal. A loop in the form of equilateral triangle with a side of 10 centimeters is placed in a magnetic field with the magnetic flux density B is equal as AT plus CT squared. Okay, where A and C are constants. Okay, the normal from the surface of our loop and the magnetic field lines form an angle beta, which is equal to 30 degree. Okay, find the energy, or okay, find the energy which is released from the time in the interval of time from 0 up to 10 seconds if the resistance of our loop is 10 ohm. Okay, again, first of all, we need to find electric motive force. So electric motive force is always equal to and not always, in our case, is equal to dphi over dt. So magnetic flux through our loop is bs cosine beta. So b is given, so we don't know s. Cosine beta is given, so we need to find s. The surface, no, the area of the triangle which is equilateral is given with the expression of a square root of 3 over 4. And if we put it to the expression of flux, we'll get for B we put a T plus CT squared multiplied. For S we put a square root of 3 over 4 multiplied. For cosine B we put cosine 30 degrees. And from this we find the expression for electric motive force. Okay, electric motive force well, again, I'm writing the absolute value of electric motive force. I skip the sign minus. So phi is equal to So AT plus CT squared multiplied by A squared square root of 3 over 4 multiplied cosine 30 degree is, well, cosine 30 degree, if I'm not mistaken, square root of 3 over 2. Okay. If we take the derivative from this expression with respect to time, we get A plus 2ct multiplied, so A squared 3a squared over 8. And if we put the numeric values, A is equal to 0.04. So A is equal to 0.04 plus 2 multiplied by C is 0.002 multiplied by T. Okay, multiplied by T multiplied by 3. The side of our triangle is, okay, 10 centimeters. So 0.1 squared over 8. Okay, we have the expression of electric motive force. Now let's compute the numeric values. 3 multiplied 0.01 over 8. Okay. 3.75 10 to minus 3 0.04 plus 0.004 t. Okay, we found the expression of electric motive force. Now, in order to find the amount of heat which is released in the interval of time from 0 up to 10 seconds, we need to find first, we need to define the expression of power, and after, if we integrate the expression of power with respect to time, we get the amount of heat which is released in the interval of time. In our case, from 0 up to 10 seconds. Okay. So, okay. Let's define the expression of power. Power is equal to electric motive force squared divided by R. R is the resistance of our loop. Okay. And is equal to 375 multiplied 10 to minus 3 multiplied 0.04 plus 0.004 t. Everything is in the power 2 divided by R. R is equal to 10. and is equal to 375 multiplied 375 is equal to 14. It means 1.4. Okay, 1.4 multiplied 10 to minus 6 multiplied by 0.04 plus 0.004 t squared. Now we define the expression of power with respect to time, pt. And now if we want to derive the expression of heat which is released, uh, we need to integrate power. Okay, so the amount of heat Q is equal to integral from T1 up to T2 power T dt, and is equal to our T1 is 0, T2 is 10 seconds, PT is 1.4 10 to minus 6, 1.4 10 to minus 6, 0.04 plus 0.004 t squared dt. Okay. Now we need to integrate this expression, and this is equal 1.4 10 to minus 6 is constant term. 1.4 10 to minus 6 is constant term, is goes out of the integral, and if we integrate we have, okay, we have 4 no 10 to minus 2 squared t plus this multiplied by this 2t, and it will be 4 10 to minus 2 multiplied 4 10 to minus 3 multiplied by t squared plus, okay, 4 10 to minus 3 squared by t to the power 3 by 3, and all this computed from t1 equals 0 up to t2 equal to 10. If we put 0, everything will be 0, and if we put 10, we may compute. So 1.4 10 to minus 6. Here 16 10 to minus 4, or 1.6 10 to minus 3, 1.6 10 to minus 3 multiplied by t multiplied by 10 plus 16 10 to minus 5 or 1.6 10 to minus 4. Okay, yep. 1.6 10 to minus 4 multiplied by t square is 10 squared plus 16 10 to minus 6 multiplied 10 to the power of 3 over 3. And if we compute the numeric value 1.6 10 to minus 3 multiplied by 10, so again 1.6 10 to minus 3 multiplied by 10 equals plus 1.6 10 to minus 4 multiplied by 100 plus 16 10 to minus 6 multiplied by 10 to 3 equals divided by 3 plus okay, we have 1.4 10 to minus 6 multiplied 3.7 10 to minus 2. 1.4 multiplied 3.7 equals to 5.2 10 to minus 8 joule. Okay, the heat released by our loop in the time interval from 0 second up to 10 second is equal to 5.2 10 to minus 8 joule. Let's continue. The next problem. The next problem is saying that again we have the same configuration as before. I mean we have the equilateral triangle which is placed in the magnetic field with flux density B, and the normal of the surface of triangle and flux density lines form the angle beta, which is equal to 60 degree, and so B is given as a t to the third power. So a is constant 0.2. The side of a triangle is a and a. So we need to find, first of all, we need to find the expression for the current with respect to time, and then we need to find the current at the instant of time when t is equal to 10. So we proceed we proceed uh, exactly as we did in the previous problem. We know that current with respect to time is equal to electric motive force over the resistance. So, well, resistance is given. Now we want to find electric motive force. Electric motive force is, again, I will write the absolute value without minus, the phi over the t, and is equal to d over the t, where phi is equal to b multiplied by s multiplied by cosine beta, and so d over the t. B is given as a t to the third power, s the surface s is given as a square root of 3 over 2 multiplied by cosine beta, and it is equal, so it is equal to so derive if we derive this expression with respect to time, we get electric motive force, which is equal to a squared square root of 3 over 2 multiplied cosine cosine beta is 60 degree, cosine of 60 degree is 1 over 2 multiplied by 3 t squared. Yep. Yes. And the numeric value of electric motive force. So let me rearrange it once more. So what we have, 3 square root of 3 over 4 a squared t squared, and the numeric value for electric motive force will be 3 multiplied by square root of 3, or better 3 over 4 is 0.75, square root of 3 multiplied by 0.75 is 1.3 multiplied. A is given as 0.2, capital A is given as 0.2, lowercase a is given as 10 centimeters, 0.1 squared multiplied by t squared. So it is simple, 1.3 by 0.2 by 0.1 by 0.1. Okay. So 2.6 10 to minus 3 t squared. Okay, we found the electric motive force with respect to time. Okay, now we can find, we may find, or we can find the current I with respect to time, which is electric motive force over resistance. Resistance is equal to 10 ohm. So we have 2.6 10 to minus 3 t squared over 10 and is equal to 2.6 10 to minus 4 t squared. And the current at the instant of time when t equal to 10 seconds will be equal. We put here instead of t 10. So 2.6 10 to minus 4 multiplied 10 to the 10 to the power of 2, and this will be equal, so 2.6 10 to minus 2 or 26 milliampere. The current at the time instant when t equal to 10 seconds will be 26 milliampere. Mm -hmm. Okay. So 75. The exercise number 75. We have the circular loop, which is okay. One moment. Let me draw it in the form of ellipsoid. We have circular loop, which is placed in a magnetic field with flux density defined as a t to the fourth power. Okay, we need to find the the normal to the surface of our loop, and the lines of magnetic flux density are parallel. It means the angle between them, alpha, is 0 and cosine alpha is 1. Okay, we need to find the radius of our circular loop. Okay, this is the radius r. We need to find the radius r if the current at the time instant when t equal to 10 seconds is equal to 1 milliampere, and the resistance of the loop is 10 ohm. So can you find the radius of the loop? So try to solve this problem by yourself. Yeah, you will be given something about 3 or 4 minutes. Try to solve, and after that discuss. We will discuss it. So please try to solve. So do you have any idea or uh, anything to say or to discuss? I don't know. Well, meanwhile, please. Okay, let's continue. What we have done so far. So we know that electric motive force is equal to minus the phi over the t, where phi is equal to b multiplied by s, where s is equal to p r squared, and electric motive and s is equal p r squared. B is equal a t to the fourth power, and the electric motive force will be equal the phi over the t, the derivative of the magnetic flux with respect to time, and this equal to 4 a p r squared t to the third power. And now we know the electric motive force we can find the IT, which is electric motive force over R, and is equal to 4 AP R squared T to the third power over R. Okay, let me copy this. So this is equal to IT, and I at the time instant of 10 seconds is equal to 4 AP R squared multiplied, instead of T we put 10 to the third power over R, and is equal to 1 milliampere 10 to the minus 3. We have numeric value of A, which is given. We have numeric value of resistance R, which is also given. And now we can find the radius, which is in our case lowercase r. R will be equal to capital R multiplied 10 to minus 3 over 4 A P 10 to the 3. And okay, let's compute this. R is given as 10 ohm multiplied 10 to minus 3 over 4 multiplied A is given as 1 over 4 P 10 to minus 3. So 1 over 4 P 10 to minus 3. 1 over 4 P 10 to minus 3 multiplied 10 to the 3. No, sorry. 1 over 4 P 10 to minus 3 multiplied by phi multiplied by 10 to the power 3. Okay, now 10 to the minus 3 simplifies with 10 to the minus 3. 4 simplifies with 4. And P multiplied by P is approximately 10. That's why P squared simplifies with 10. And the only thing remains is 1 over 1000, which is approximately 0.031 31 6, or meters, or approximately 3.2 centimeters. Okay, the radius of the loop we found is 3.2 centimeters. Okay, the today's lesson is over. Tomorrow,
이게
yes,
그 B대 카드가 되고 하더고
one moment. I will stop the video.